So in this case, we are going to consider an introduction, which is actually the basics of our module 6, working with the stress, strain, and the Young's modulus. So if we are to consider the part of stress, which is the major part that you're going to have, which is the stress and strain. So we are going to consider, or we are going to see that later on, these two, they work hand in hand. They do work hand in hand. So whenever we are going to be referring on the stress, at the same time, we are going to consider the strain in the calculations. So later on, we are going to consider the Young's modulus of elasticity, which we are going to look into consideration later on. So on the basics of our syllabus, they want you to understand these two, the stress and strain that are under the first one, which is called the direct. So we can have these two under direct, which is direct stress and also a direct strain. The same stress and strain that we are referring to can be calculated under what we refer to as the shear. So there, we shall be working with the shear stress. Later on, as where the shear stress is, meaning to say we are also considering the strain which is affected by the shear stress. So as the major part of our class today, we are going to consider the direct stress and strain. Then we are going to see later on the shear. So basically, when you consider the stress, as we have got our definitions, remember, the definitions are also going to help us in realizing or in the calculations later on that we are going to have. Despite to say this is a direct stress or this is a shear stress that we are considering, just what is it that we refer to as the stress? This is the ability of an object to resist the effects of an external force and is given by the amount of load per unit area. So let me just have this statement. So I'm saying this is the ability. So that's the ability of an object to resist. So this object must resist the effects of an external force. So that's the effects of an external force. And is given by the amount of load per unit area. All right, and is given by the amount. So this is what we're going to have there. The amount of what? Of load. So this is the amount of load per unit area. So I want us to consider as part of the class that we are having, which is the direct. So when we are considering now the direct stress, still we have got the same thing. The definition there is still the same. But what we are going to see is that when we have got a direct stress, a force is being applied to an elastic body. The force will then deform or try to deform the body. That is the state that we are now having, where the force will be resisted by internal forces caused by the cohesion between the molecules of the material. So that is the major part now of a direct stress. So do not worry, guys. The issue there is just on the calculations there to be made. That is the major part. All right. So let me have also for strain. Then we can consider the calculations quickly. So let us quickly consider the strain. Like I said before, the stress and strain, these two, they go hand in hand. So we are going to see that the strain now is the deformation of an object due to an internal state of stress, due to an internal state of this. So that is why we say they do work hand in hand. So that is the deformation, this one. So it is the deformation of an object. The deformation of an object due to an internal state. The internal state of stress. That is from the stress that we had. So if we see on these presentations, I'm not referring to the symbols, because when we just say stress, it is just basically can be under direct or it can be under a shear. So as we consider the direct stress now, the direct stress, as we consider this one, the issue now is on the symbols that we are going to have. Like I said before, to say when a force is applied to an elastic body, the force will deform or try to deform the body. That is the condition of a direct stress, which can be a condition where a tensile force is being applied. All right. The one which tends to make the body larger than what it was. Let's say this is what we had. Then we are experiencing a tensile force. So where there's a tension, this one is tended to take this side, this one is tended to take this side. So it makes the body longer. It is under a direct stress. Then we also consider the compressive, where a compressive force is being applied, which then makes the body to be shorter in terms of the size. Because in this case, we are pushing towards the center. Like it is compression, compressive from compression, if we just basically from the word compress. So at the end, this body will be smaller because it has been compressed, becomes smaller at the end. Where the tensile force was, the body will become bigger at the end of the day. So you need just the basics there. Just the basics. I do not even worry about, say, okay, this, no. The basics are the ones that you just need. All right, so like I said, as we are working with the direct stress, the symbol that we are going to use is the Greek letter sigma. So we are going to use the sigma, all right? So that is when we work with a direct stress. We are going to see for a shear stress, we are going to have another symbol to use there. It is still the same stress that we are referring to, but only the symbol. So there we are going to use the sigma. So these are just Greek alphabets, guys. It is just like us, we are using those A, B, C, D. All right. So there they can use even letter A, letter B, but you know, guys, whatever that we are learning, taken from what? From the Greek. So that's it. That's what we have. So at the end of the day, we just have to consider their letters, their alphabetic letters, but we could have had these symbols even written in the way that we understand, because we have the alphabet that we use, the one, the English one. So I don't know why do they still use um these symbols by now. Anyways, that is what we have. So the stress, which is considered as the direct stress, can be taken from the formula, the force over area. So we are going to consider the force over area. So as we do understand the units, guys, force over area, force in Newton, here, because this is over a what? Area in square meters. The unit Newton per square meter, it is not the first time that we are hearing about this. We do understand that it is actually equivalent to a what? To a Pascal. So when this is 1, this will be equivalent to 1. A Newton per square meter is equivalent to what? A Pascal. So meaning to say the units, or the unit that you're going to use is the Pascal. So that is our direct stress. So you consider the direct stress, which can be under a tensile force or under a compressive force. So if you are the one who is to mention, all right, you want to mention it was under a tensile force, it is up to you. You can use the letter T there. It was under a compressive force. You can use the C there to indicate that it was taken from which type of force at the end of the day. But that is not important, okay? You can even ignore that one. So just make sure the area is in square meters here. This area is supposed to be in square meters. So calculations of the areas depends on the body that you are given where the force is being applied. The force can be applied on a rectangular body. So consider length times width, area. It can be applied on a circular body. Consider the area of a circle, pi. You can use the pi r squared, or you can use the pi d squared over 4, depending with information that you are given there. Where is the force applied? You must consider the type, all right, the shape that you are given. If you are given that it is a rectangle, then you consider the area of a rectangle in square meters. And also conversions, guys, let us do understand our conversions, because in most cases, they are going to give you dimensions which are maybe in millimeters. Most cases, millimeters. You have calculated, maybe this is 5 millimeters, this is 4 millimeters. If you are to convert to decimals, guys, you've got something like 0,005. Imagine these values that you're working with. So sometimes you decide to work with the millimeters as they are. Then just convert to the square meters, because at the end, our area must be in square meters. So how do we convert? That is the case. So if we are given the square millimeters, all right? Let's say we are given something that is in square millimeters. For us to convert it to the square meters now, we are supposed to multiply by 10 to the exponent of -6. Our answer will be automatically in square meters, which is the opposite or the vice versa of what we're having. So what am I trying to say here? In some cases, you might find out that you have got written your answer, let's say, You have got something like 7,126 times 10 to the exponent of negative 6 square meters like this. I just want you to understand something like this. You have written your answer like this. I'm not saying it's wrong. It is your final answer, this one, which you can decide to leave it like this. Or you can decide to change it to the square millimeter. Because as we can see here, whatever that we are having, but having this times 10 to the exponent of negative 6 in square meters here, this part, it is a direct equivalent of what? Of a square millimeter. So meaning to say, wherever we have this, we can even change this one and write as 7,126 square millimeters, because this whole part here is equivalent to a what? A square millimeter. So you see, guys, some of the things that we must consider as we are doing our calculations. So the rest, guys, it is in your hands. Also, as we are going to have these topics, there is this issue of the pi. Most of us have been asking in some revisions, because we had this topic before, there's question papers. So most have been asking the issue of the pi. Say in some textbooks, you'll find out they will give you, take pi to be 3.142. Guys, you are working with your own reference there. This is your textbook. Use that as it is. It does not mean necessarily that if you are in an exam condition, you must use the pi as 3,142. No, that was what you were given by your textbook. It is your textbook, guys. Exam is something else. You are told use pi as, you take it as that one. But for exam, where pi is, and you're not told about that pi, use the pi on the calculator, the one that you're having on your calculator. So I hope on this part we are clear. We work with the instruction that we are given from the reference that you are using, all right? Because your textbook is different from someone's textbook does not even mention about that pi as 3.142. They just use the pi as it is on the calculator. So the reference that you're using. So this is it, guys. Like I said, the stress is being calculated. It is measured in what? It is measured in pascals. So that is what you're going to have. And I mentioned before that wherever the stress is, the strain is also to be calculated. We saw that these two, they go hand in hand. So in the same sense, we are going to have the formula for the direct stress. I mean, a direct strain. So a strain, all right. So let us just have a direct strain here so that we can quickly finish and have examples. So when it is a direct strain, we are going to use the epsilon to indicate what is the symbol there for the direct strain. That is epsilon. Epsilon. So guys, the way that these are Greek, guys. These are Greek terms, Greek alphabets. All right. So that is the one that we're having there. It is the change in length per unit length. So guys, it is right, the change in length per unit length. So if we say the change in length it means there was an original length, just like the part of when you deal with heat. We are going to see that part on heat. When the heat is being applied, the temperature changes. We had that change in length from the original length that an object is supposed to be having. It is having its original length. But due to the applied force, the shear has been applied, this object is transformed. There is an extension from what it was before. We are now seeing this body, maybe it has been extended like this from the original part that it was this one. It was indicating the original length, this one, this L. But it is extended by some length. So that extension, this one, is the change in length. So the change in length, you can also just write as X. You can just use the X there, or you can just write as like this, depending with your textbook also, guys, how they indicate that change in length. Some they just use as it is, change in length as it is. That's the change in length. So meaning to say, together from the original length, combining with the change in length that occurred, we are now having the final length. So it is simply the original plus the change in length. That's the concept. So anyways, guys, this is another part. Here we want to consider about the direct strain. So the direct strain, as it is given on the formula, change in length. Per, meaning to say over that, change in length per what? Per unit length. It simply means per that length that you're given. Which length is it? That is the original. So here we are referring to the original length. So as we have it, guys, here, the change in length, that is our extension, the change in length, over what? The original length, which is our L. So depending, like I said, with your textbook, sometimes they just use L over original length. They use as L or like this, depending with the textbook that you're using. That is basically what will be happening on the application of the direct strain. So without wasting our time, guys, let us quickly go through some of the examples to cater up for these two that we had been referring to, the direct stress and also the direct strain. So on this question, we are given a mass of 250 kilograms hangs on a 4.5 millimeter round bar. It hangs, meaning to say the gravity has to be considered. Gravitational acceleration. So anyways, calculate the stress in the material. So from this concept, you are referring to a direct stress. When a force is applied to an elastic body. Okay? So that is basically what we have. So we are given the mass according to the information, 250 kilograms. Also, the G you use according to the one that you're given from your textbook. All right. So as for exam purpose, remember that our G, 9.8 meters per square second. So it hangs on a 4.5 millimeter round bar. That's a circular So we are given its diameter, which is 4,5 millimeters. So like I said, you can convert this to the meters. It is up to you. Or you can work with the millimeters as they are. So, okay, let's say you do write this in meters. Remember, it's going to be 4,5 times 10 to the exponent of -3. Like this in what? In meters. Converting or having a decimal, guys, 4,5 times 10 to the exponent of -3, it is something like, you're having something like this, 0,0045. That's 1, 2, 3, yeah, something like that. So working with this decimal alone, guys, this is too much. So we can avoid and just work with the millimeters as they are. So I want you to consider that one. Okay, I want you to consider that part. So the diameter is going to help us to calculate the area. Okay, no problem. So here the question was to calculate what? The stress, which is the direct stress, which we said it is going to be force over what? Over area. So we do not have the force, we do not have the area. So force is going to be calculated from where there is mass and the gravitational acceleration. So we can calculate our force from there. That is mg from our sines n3. So the mass is 250. Our gravitational acceleration of 9,8. So that was going to give us a force of 2,450 Newton. All right. So we've got the force this time. Then the area from the diameter, that is pi d squared over 4. So like I said, we can even use the millimeters as they are. So that is pi times d 4,5 squared over what? Over 4. So take note, this is in what? In millimeters. So whatever answer that I'm going to be having is or be under millimeters. So that was going to give us something like 15,904 like this, square millimeters. So we are not supposed to be scared about the square millimeters. Just because the area is needed in square meters. Why? Because we know the conversion between the two. From square millimeters to square meters. We're simply going to multiply by what? 10 to the exponent of -6. It will be under square meters. We simply have to multiply by 10 to the exponent of what? -6. So this one, it is not an issue. Just leave it as it is. All right, so let's go back to the stress, guys, and answer the part. So gonna have the force 2,450 over what? The area. Remember, whenever we are to substitute back here, the area must be in square meters. Do not forget now to say here, area is not square meters always. That is why we must convert this, multiply by what? 10 to the exponent of -6, like I said before. So you're going to just take as it is. That was 15,904 times 10 to the exponent of -6. So multiplying here by 10 to the exponent of -6 is converting to what? To square meters. So that's it. We are going to obtain our stress in what? In pascals. Like I said, whatever that we have here is going to be in what? In pascals. So this is it, guys. Whenever you are doing these calculations, okay, I want you to see something. Let us have our calculator so that we do not assume something here. You are going to insert your values 2,450 like this over what? 15,904 like this times 10 to the exponent of -6. This is what you got. This is what you have. So if we look at this value, guys, then we've got so many digits there. So it will be best that we have our answers for direct stress, guys. Megapascals will be best. It will be best for our conversions to have them under megapascal. So the question is, how can we convert now to the megapascal? Because as it is like this, the answer here that we can see is having a lot of digits there. So megapascal means times 10 to the exponent of negative or positive 6. I mean, this one. That is what it means. So how do we convert to it? If it means times 10 to the exponent of negative 6. So how then do we convert the answer that we have on our calculator to that? We multiply by the opposite now. So what is the opposite? Times 10 to the exponent of a negative 6. Remember, megapascal, it's a positive 6 there, times 10 to the exponent of a positive. So the opposite times 10 to the exponent of a negative 6 will automatically convert our answer to what? To megapascal. This one, it will automatically give the answer that we are seeing on our calculator there in megapascal. So let's do that. Times 10 to the exponent of negative 6. Let's do that and see. So this is what we're going to have. 154, what? All right, let's just remove that. Okay, let's like this one. So it's gonna be 154,049. Okay, automatically like that. 0.549 under what? Megapascal. So this is what I said, guys, before for all those conversions. For those who are following our classes, I think now we are much updated when it comes to the conversions. You multiply by the opposite to express your answer to a certain unit. To express your answer to a certain unit, you multiply by the opposite of the unit. The opposite of the unit, I simply mean the sign. If it is kilo, it means times 10 to the exponent of what? Of 3. So when I say the opposite, guys, I simply mean what? Negative 3. The same way, if it was a negative, you just use a positive. Your answer will be to those units. All right. Anyways, that was it on this question. You saw that sometimes you might not be given everything at once. You have to calculate the force. You have to calculate the area. Okay. And the questions can further even extend where you must calculate even the strain, provided that there is what? There is an extension that you are given, which is the change in length. All right. Another question. We were given that calculate the tensile force. Like I said, as we at work with direct stress, it can experience a tensile force or it can experience a compressive force. So meaning to say, when they say calculate a tensile force, it means the stress here that we are given, it is a tensile stress. But don't worry about that. You can indicate that way, or you can just indicate your stress as it is, guys. We are given the stress of what? 20 megapascal, and we are asked to calculate the tensile force which is affect this in a rectangular steel rod. Rectangular. These dimensions are from what? A rectangle, where we do understand there is length and width, or length and breadth. So it has dimensions of what? 24 millimeters by what? 18 millimeters. So from there we can have the area. Okay, anyways, the question was to calculate what? The force. So remember, we have got the stress, which is actually a tensile stress according to the type of force that you're given. So as we have got force over area, we need the force. So simply cross multiply, guys. If you cross multiply here, force is equal to what? We multiply. So 1 times F, that's force, is equal to these two, they multiply. So that's going to be the stress times area, where we are given this and area we do not have. So we are supposed to calculate the area from what? A rectangle length times width. So that's it. In millimeters, 24 times 18, that was going to give us 432 square millimeters, which can be converted to the square meters. The reason being, as we have got the formula here, this area on our formula must be square meters. Do not forget that. So let's substitute. The stress is already there, 20 megapascal, 20 times 10 to the exponent of what? Of 6. We are not converting anything, guys. We are rewriting the megapascal here. Here, we are rewriting. It means what? Okay, times the area to, now we have to convert this what? To what? Square meters. So how do we convert that? 432 times 10 to the exponent of negative 6. Remember what I said before. By multiplying by 10 to the exponent of negative 6, your answer will be automatically under square meters. So this conversion is to have our area in square meters. All right. So this was now you and your calculator to obtain the force. That was going to give us 8,640. So also, guys, use your calculators to confirm, because, you know, errors can happen as you are working with calculators. But as an individual, also try to figure out with your calculator to see if we are on the same page. All right. So we're looking into another question. That is question number 5. A steel rod, it has a diameter 12 millimeters and 2.4 meters long, the length of the rod. So the length of the rod it has, where it is, the way it is got its own effect. So this is like we've got, what do we call this? A cylinder, something like this. So let me just have a sketch. It'll be a cylinder, this one, okay? So it is something like this, where we have got a circle here and a circle here. So they are saying the diameter in this case is what? 12 millimeters. This is our diameter. Then the length, that is how long the rod is. How long, that is the length of the rod now that we are considering here. So that is the one that we are given as what? 2.4 meters. Is extended by 0.3 meters. There is an extension which occurred. Do not know which side, but there is an extension that occurred. And they gave us that extension. The extension is simply what? The change in length. So we are given also the change in length. This is the data that we have. So the change in length is what? 0.3 meters. So this extension was caused by a force of what? Of 30 kilonewton. So we are given a force. So the question was then calculate A, the stress. So the stress, guys, from the area part of the bar, the area part of the rod from the diameter there. That is where we must have the direct stress. So as we hear that our direct stress being force over what? Over the area. The force is already given. We have it. But the area now from where? The diameter. So you're going to calculate your area first. So area, remember that's pi d squared. Pi d squared over what? Over 4. So that's pi times, using our diameter. We can even All right, for the sake of calculation, we can even just, let me write it down. This is our diameter. Can write as what? 12 squared over what? Over 4. But know that whatever that you're going to have here is going to be in what? In square millimeters. So some, because you've got another answer, then another answer, you can even just substitute as it is the force. Remember that is 30 kilonewton times 10 to the exponent of what? Of 3. The area is this, which is pi times what? Times 12 squared, like this. All right, so this is pi times 12 squared over 4 times, remember, this is square millimeters, but we need this area to be under square meters. So we must multiply by what? 10 to the exponent of -6. Just like that. Guys, understanding this and understanding your calculator also is important. There will be no need for you to express this. Okay, I'm not saying it's wrong. To have this as what we've been having before, that you calculate the area aside. No, it's not wrong. It's correct. It's fine as it is. But we can also have this in a shorter way by knowing the formula, then just substitute as it is. Also, by understanding our answers, like I said before, we do understand whatever that we have to calculate here, which is our stress. It is best for us to have that answer in megapascal, but that does not happen. How are we going to have our answer in megapascal? I said you are supposed to multiply whatever that is in your calculator that you are seeing on your calculator. Multiply it by what? By 10 to the exponent of -6. Automatically, your answer will be under megapascal. So let's do that, guys. Take our calculators, simplify everything. You are going to have something like 265,224, which is in what? Megapascal, already converted to megapascal by this one. So you must be very careful. Knowing your calculator, knowing your formulas, very, very important. Is very, very important. All right. Anyways, without wasting time, let us quickly have this one, which is the B part, the strain. So the strain, as we saw from the formulas, it is from the change in length and its original length. So this one was a direct question because we have got the two. We have got the two. So B, that was the strain. So the strain, the change in length over the original length. So the change in length, 0.3 meters over what? 2.4 meters. You must be careful about the units here. Since it's a division, same unit so that these two can cancel. So if you're given millimeters, make sure that both are in millimeters. Make sure that both are in millimeters. So that's it. So that was going to give us 0.125 as a decimal. So I want you guys to do as many questions as you can, do revisions, question papers, and also not forget to join membership so that you do have many revisions, like preparations for your exams, which are ahead of time. So that can help us as we do our preparations. But I think, guys, that is it for this class. We are going to have a continuation, like I said, considering the shear stress. So just one or two things that you need to understand there. But the basics in terms of the units, some of the basics of the formulas, you have them. And as we can see, the strain is unitless. As we cancel the unit, if meters cancel, so we do not have the units for this one, right? So same if it is millimeters over millimeters, those two, they cancel. So at the end, you do not have units for strain. So that is it, guys, for this class. We shall meet again in the next one. Till we meet again, guys.